boron on the periodic table. So remember, you have a periodic table. Those of you over here find it too much work to look at the periodic table provided to you in your packet because y'all are keep like. But those of you over here, especially those of you who can't see as well as others, it's going to be hard. But find nickel and find boron and see if you can find which one is an alloy of nickel and boron. Go ahead and have that discussion with each other.
But I can see nickel and boron on there. Neither do I. I think we have boron as a number. Let's go to I'm missing.
I'm assuming.
I think
I don't do it, my AP class is not just for their population. This is multiple choice, but on every single test, they can do one of these, always it's an easy thing if they understand it. And they don't even have to know the word.
So if you have the metal,
because it's not a B, it's like you can't, you're going to fit things in between here.
Alright, can y'all tell me definitely what it ain't?
B!
Can't be B.
dang.
Why can't it be B?
Because they're all the same.
They're all the same. It's not an alloy at all. It's just one thing.
this AP test is messed up.
Okay. Now let's see if y'all can figure out the interstitial substitutional. That one right there. Is that interstitial, letter A, or substitutional?
Substitutional.
We took something out, we replaced it with another. Down here, in letter C, is that substitutional or interstitial?
Interstitial.
Nice. And this one down here on the end? That's substitutional, right? Okay. So what did y'all come up with for an answer? What do you think it was? C? Why?
Because boron is a non-metal.
Okay.
So you have to substitute.
And I mean, that is true. But it's sunny outside and today is Saturday. Right? So, just because it's a non-metal, I don't know why that gives you backup. Like on an FRQ, if you had said, it's got to be this because it's a non-metal, doesn't really talk about, because you've got some big non-metals and some little non-metals, right? Some of them are bigger and some of them are smaller. So, that would not be cause enough. What did you...
But like, you'd have, but not because it's not, but like.
Right, y'all do this for me. What row is nickel in? Fourth row. How many layers of electrons does it have? 4. What row is boron in? 2. How many layers of electrons does it have? 2. So which one's going to be bigger, the boron or the nickel?
Nickel.
It's going to be the nickel. So first of all, you want to pick one where one molecule is definitely bigger than the other. Right?
It's not A.
So, A, they're exactly the same size. B, we've already determined can't be it.
A is not the exact same size.
Well, A is one is actually bigger than the other, but just by barely, right? Okay, and we're looking for a profound difference in size. So the correct answer ends up being C, largely because boron is going to be much smaller and nickel's going to be much bigger. Now you said that boron's a non-metal, and I'm with you. But see how boron sits right on the edge of where the metals start? And we call the things that kind of hug that stair-step line between the two, we call those metalloids. A little bit of both. So kind kind of like Caitlyn Jenner. A little bit of both, right? So, well, y'all know who that is. All right, kind of a little bit of both, right? So, same thing here. So I wouldn't call boron necessarily a non-metal. It has certain properties that are kind of metallic-like. But this all has to do with kind of you got little tiny atoms and great big atoms, and that's really what you're looking for between nickel and boron. Yes.
Some question. What if they were like both on row 2? How would you determine?
If they were both on row 2, you would expect them to be the same size.
Okay.
So it's going to really be hard to make them interstitial. Okay? So I can take, if you're sitting next to somebody in a car, you got 3 across the back seat. I could probably take a baby and put it between 2 of you. But can I sit there? No.
Okay.
I'm a big molecule. I cannot be interstitial. I need to be substitutional. Get out of the car and give me your seat.
Okay.
Right?
So then would one look bigger than the other? Like
If they're both on row 2,
they're not going to look bigger than because I did the same.
they're going to be about the same size.
So it'd be hard to decide.
Well, I'd be picking this one
Okay.
because they're approximately the same size.
Okay, I was just wondering.
And trust me, they're trying to make it painfully obvious that one is bigger than the other.
Okay.
I mean, they picked nickel and boron. They could have picked, nickel and like arsenic or something like that. But they're trying to go out of their way to show you that. Right. What makes something molecular? It has molecules. Good. All right. Well, let me give you a hint. How do you know if something's metallic? If it's a metallic solid.
Oh,
It's all metals.
yeah.
How do you know if something's ionic? It's a metal and a non-metal. Now you see where I'm going. How do you know if something is molecular?
It's non-metal.
Just non-metals tied together with those covalent bonds. So, who is your favorite covalent or molecular solid? You have a favorite? Which one?
Water.
Water, sure. Ice. You make another one? Sugar. C6H12O6. Sure. Anything else?
Oxygen. No, carbon dioxide. No, I don't need that.
Oh, dry ice is a great one.
I don't need
Right?
that.
Okay. You don't need carbon dioxide? All right. So, these are molecules that internally are covalently bonded. But externally, from one molecule to another, are fairly weak bonds. So, we'll go back to iodine and iodine. Covalent bond, some kind of weak intermolecular force holding them together. So covalent things, molecular things, tend to have fairly low melting points. Because you're not breaking that covalent bond, you're breaking that hydrogen bond or London dispersion force or dipole-dipole. And so they're fairly weak. So what temperature does ice melt at?
100 degrees Celsius.
32 degrees Fahrenheit, 0 degrees Celsius. That's when water freezes, ice
I
melts.
was thinking water.
Same thing, right? Boiling 100, right? All right. What about something like carbon dioxide? You mentioned carbon dioxide. Dry ice. When does dry ice boil?
200.
You ever played with dry ice before?
Yeah.
If you haven't, you should tell your teacher. We really need to play with dry ice so that I can understand molecular salt. Look at y'all. Look at y'all. Cast. Wow. Wow. Like. You can buy it at Publix. It's adult. Well, no. Sorry. You can't buy it at Publix. Your parent can buy it at Publix. If you're 19, you can buy dry ice. But dry ice. Yeah, you can buy it. So it's got a penguin on it. Right there at the front of the store, like a cooler. They got anyway. The dry ice boils. It turns from a solid straight to a gas. It sublimates at like negative 70 degrees Celsius. And that tells you those intermolecular forces are crazy weak. Right? Right. So let me see how much y'all know about organic chemistry. Okay. All right. What's the formula, or what state of matter is propane under normal conditions?
Liquid.
Under,
That's just in your car.
no, propane is like on your gas grill.
Oh, that's,
It's a gas.
that's like fish fry, whenever you eat your fish fry, go in here.
Yeah, okay. So it's a gas, but then we store it as a liquid in those tanks, in those big metal tanks, right? What about octane? You know what state of matter octane is?
Yes.
It's a liquid. And we find it in gasoline. That number, 87, 89, 92 that's on the gas pump, that's a measure of how much octane is in there. Octane is a liquid, and asphalt. You all know what the formula for asphalt is? C1000, H1003, something like that. It's a really big molecule and it's a solid. My point is, all of those molecules have London dispersion forces. But the bigger they are, the harder they are to melt. The bigger they are, the more intermolecular forces they have. And yet, they're all molecular solids held together with these London dispersion forces. So, what y'all need to know is this very simple fact for molecular solids. The more electrons you have, the more London dispersion forces you have. That's because and this is a real word. It sounds like I'm making it up. But when you have more electrons, you are more polarizable. Meaning, it's easier to create a London dispersion force. So the bigger you are, the more London dispersion forces you have. So propane is C3H8. Octane is C8H18. The bigger you are, the more intermolecular forces. Methane, only CH4. It doesn't have very many intermolecular forces at all. So the more electrons you have, the more intermolecular forces. All right. What do y'all know about liquids? Cats are liquids. They take the shape of their container.
They do?
Liquids do, not cats. Well, that cat does, yes. But liquids take the shape of their container. So do gases. Solids do not. Water versus ice. Right? Now, just as a reminder about gases, what do you all know about gases in general? Here, we'll come back.
Is
So
it
y'all-
infinite volume?
Right, they will live in whatever volume you give them to live in. What else? What do you know about how close together gas molecules are? They're really far apart. What do you know about their movement? It's very random. And what do you know about their kinetic energy of a gas? The energy from movement. What do you know about it?
It's higher than the states of matter.
It's higher than other states of matter. A little nebulous. What happens to kinetic energy when you warm something up? It increases. So the warmer you are, the more kinetic energy, the faster the molecules are moving, the warmer you are, the more kinetic energy you have. What if you have no energy at all? Absolute zero. How much are you moving?
None.
None. Don't tell that to a physicist. They will just talk your ear off. They start drawing equations and stuff. She said it's not possible. And I was like, certain things to say. Like, you don't look at my wife and say, wow, have you gained weight? Right? You don't say that, right? So, just certain things you know that will get you into trouble.
And don't
Right.
ever smoke.
That's right. So all the molecules are really far apart. The important part also is when things run into each other, they're perfectly elastic. In other words, when they bounce off each other, there's no energy lost. So that would be like, you ever play pool? Imagine hitting the pool balls and they never slow down. They just keep,
Oh my gosh.
because there's no energy lost to collision. The average kinetic energy is proportional to the temperature. They expand to fit their container, and you can smush or compress a gas. And hopefully that's kind of just a reminder for y'all of gases. Alright, so look at question number 4 for me. And go ahead and have that discussion, I think on y'all's printouts. Alright, so, let me borrow this for a second. This is ethanol right here. The CH2, or CH3CH2OH. And the dimethyl ether, the structure didn't really end up where it was supposed to be. So the only difference between the ethanol and the dimethyl ether is where the oxygen is. So the ethanol has the oxygen on the end. The dimethyl ether has it in the middle. That's all you really need to worry about. You should not know how to name dimethyl ether because none of anybody care. They'll give you the structure with the name. So your job is to just look at it and talk about it. Go ahead.
Hey, so thank you for being here. We're gonna give away a $10 Amazon gift card.
Oh, thank you.
There are 30.
And a roach. Get a roach stage.
33.
We found one on the floor.
Okay, I'm not gonna tell you what I was thinking.
No, not that,
Yes,
no.
that kind of rush.
It's early.
It's gonna be
Alright.
botany is what class.
33 names on the list. Random number generator. Number 15.
Number 15 belongs to Jacob Poole. There he is.
$10 gift card. We just need you to print and sign your name for
Look at his
legal
wrestling
purposes.
shirt. That's really awesome.
It's not the wrestling I watch.
I needed that for protein.
Yeah, but I mean I said wrestling.
Kindle books for everyone.
Yeah.
$10.
Hey, I know some of you feel bad, you know, it can be a dark place. You can kind of feel lonely. Just
Don't feel
remember,
lonely, there's 30 other kids in here who lost.
you want a biscuit in a lukewarm bottle of water.
And some of you got jelly, Mr. McWana had to share his jelly.
I saw someone who get a napkin. Winners, you're winners.
Good job, good job. Way to be positive.
We're all winners.
Yeah, there's no money for us.
I know what it is. No, I didn't.
Alright, y'all are finding an answer, correct? Or, at the very least, if you can't find an answer, find out what the answer ain't. Right? If you can get it from 4 choices to 2, that's also a great thing to do.
They're not gonna say the same thing. So it's gonna be that. Won't be easy to do the same things. Is there 6? Okay, then you can leave that in. The specific heat would be this.
Hey, what's up?
It's a good question. I definitely remember what paper it was. Alright, so, can y'all tell me something that you definitely know it's not?
I'm pretty sure it's not these, but like, we don't know.
It's definitely not D. Because when you look at the boiling points, are they even remotely the same?
No.
Since the boiling points aren't remotely the same, we would also expect the melting points to be different. Yes, sir. Okay. Anything else you want to get rid of?
Don't say that to C.
Yeah, I think the answer
Or
is
it
A.
says C.
Okay, you think the answer is A, right? All right, so we're going to show you the answer and then we'll come back and talk about why that is. So the answer is A. Now, let's walk you through. Melting points, we already did. Melting points can't be it, right? Specific heat. Do y'all know what specific heat is? Okay.
I remember hearing about it once.
Some of you may remember, Q is equal to MC delta T.
Yes.
Okay. MC, C is the specific heat. What you got?
Do you have any extra packets?
I give to Teresa across the hall.
Okay.
So Q is equal to MC. C is the specific heat of water. It's a measure of how much energy does it take to make it change temperature, which has everything to do with intermolecular forces. Okay? So, since the intermolecular forces are going to be different, the boiling point's different, the melting point's different, then the specific heat's going to be different. Vapor pressure at the same temperature. Y'all remember what vapor pressure is?
No, like the,
I'm guessing no, but y'all tell me if you know.
oh, that's the pressure. Yes, it is the pressure.
It is the pressure,
Wait,
you're right.
it is the pressure. Wait,
So-
see real quick.
Vapor pressure is just this. If you leave something out, there's enough energy for some of those molecules to turn from a liquid state into a vapor state. And when those vapor molecules bounce around, we call that vapor pressure. Now, what if you have lots of intermolecular forces? Are they held tightly together or not held tightly together? They're held tightly together with lots of intermolecular forces. How much energy is it going to be to take one of those and knock them loose?
You have to have.
You have to have a lot of energy. So the more intermolecular forces you have, the less vapor pressure. So let's give you two instances. Does water evaporate?
Yeah.
Sure. It gives off a vapor pressure. Does this desk evaporate? No, that would be weird. Right? You come in one day and you're like, does that count as dinner? Because it got warm in here and it evaporated. Got warm in here, right? She's been fanning herself the whole time. Got warm in here and evaporated. You ever notice how your driveway gets smaller every year because it evaporates away? You ever notice that? It doesn't. Because those are super strong forces. It gives off no vapor pressure. You ever had an ice cube in the freezer there so long it just got smaller and smaller and smaller? You can actually have ice cubes in the freezer that don't ever melt, but they get smaller. And that's called sublimation. You turn it from a solid directly to a gas. That's because it's giving off vapor molecules. So when you don't have very many intermolecular forces at all, you give off lots of vapor pressure. So the key here is, since they have different intermolecular forces, this guy is going to be able to hydrogen bond, and this guy can't. So this guy is going to be hydrogen bonds and London dispersion forces. This guy is only going to be London dispersion forces. And we can argue about the dipole-dipole, but the fact is, since they have different intermolecular forces, they're not going to have the same vapor pressure at all. So the answer is A. All right, kinetic molecular theory we kind of already talked about, because we talked about molecules are moving, the hotter it is, the faster the molecules go, kind of a thing. So all this is saying is that everything's always moving, and the warmer it is, the faster they're moving. Everybody get that? All right, so I'm going to test your chemistry knowledge. What is the freezing point of water? 0. What is the melting point of ice? Also 0. How can that be?
It's
Because it is. Oh, now I understand. All right, let's do this. You're taking ice molecules that are negative 20 degrees. You took them from the freezer. You start warming them up. What you're doing to those molecules is you're making the molecules move faster. When you hit that magic 0 degrees when they melt, you're not using that energy to make the molecules move any faster. You're using that energy to break the bonds. So you're not making them move faster at that point. You're breaking the bonds, allowing them to slide past each other. So at a freezing point, all that energy is doing is either going into breaking bonds, or if you're going the other way, if you're going from a liquid to a solid, that then energy is being created by making bonds. Same thing with boiling, and same thing with melting. When you're doing that, you're breaking or making bonds. You're not making the molecules go faster. So how can they be the same temperature? Because we know temperature is how fast the molecules are moving. So even though we're adding heat to it, the temperature doesn't change. We're not messing with the molecules, we're breaking those bonds. That's why the temperature doesn't change. Right? Now, have y'all ever seen a phase diagram like what you see on your paper? This one's kind of hard to see.
Yes.
Okay. Right? So let me ask you the question. Does it take more energy to melt it, or does it take more energy to boil it? Just looking at the graph. Does it take more energy to melt it, or does it take more energy to boil it?
Boil.
Why do you say boil it, besides the fact it's got numbers on it?
Never mind.
Just looking at the graph.
It points upwards.
Okay. Look here. Right? The bottom, the x-axis is heat added. So it took this much heat to melt the sample of ice. This much heat is how much it took to boil the same amount of water. Since energy is your x-axis, you go, wow, it only took this much. And if you carry that same thing up here, it's almost 3 times as much energy to boil it. Okay? So just by looking at the graph, you can say, hey, I know it took more energy to melt it, to boil it than it did to melt it. All right, 2 words that y'all need to know that are weird. Frost. Ever heard of frost before? How does frost form on your car? Not that it's ever going to be cold again in Alabama, based on the weather this week. But how does frost form on a car? You ever? Well, condensation would mean your car gets wet.
And then it gets cold enough.
And then it gets cold enough to freeze. That's when you get that annoying layer of ice on your car. Frost is different. So frost is something called deposition. It's where water vapor turns directly into a solid. So you get tiny little snow crystals on your car. Right? You also get frost in a freezer. You get water vapor, skip the liquid phase altogether, and go straight from a gas to a solid. That's called frost. The opposite of that, going from a solid straight to a gas, is called sublimation. And ice cubes do that in the freezer. Remember how I told you they get smaller? They don't do it by melting, they actually do it by giving off gas. Alright, so just 2 words for y'all to know. Sublimation, sublimation solid to a gas, deposition gas to a solid. Alright, look at question number 5 real sorry, number 6 real quick. I want to skip 5 and come back. If we have time. Look at question number 6. See if you can figure out where the solid and the liquid coexist. At what part of the line? All right, can y'all tell me at point P, what is the state of matter? Gas. And at point T, what is it? It's a liquid. And you know that because in the question it says sorry, my bad. Totally wrong. A sample of solid naphthalene is heated to 95. So this is a liquid up here. And this is a solid down here. Because you're melting it and then you're letting it cool down until it resolidifies. So can y'all tell me where it's melting? What point does it look like it's melting? What did I tell you happened at the melting? What are you using the energy for at the melting time?
Breaking bonds.
Breaking or making bonds, right? What are we not doing to the molecules? We're not messing with their speed. Therefore, anytime you're melting something, the temperature stays the same. That's why the ice is 0, and when it turns into water, still 0. So anytime the temperature is the same, we see that it's melting. Okay? So where would you say on here it's melting? R to S. Okay? And technically the question would be here, Q to S, because there's a weird thing out there in the world called supercooling. But what's the best answer on there? What's the best answer on there? Point Q, point R only, all the points between Q and S, or all the points between R and T. There's only one answer that really, this Q to S thing is kind of where you get all of them existing at the same point. All right, so do this for me. Look over at page 51 for me.